So we'll start with a quote. Our whole life is solving puzzles. And this is a quote from Erno Rubik. You might recognize the name Rubik. He's the person who created the Rubik's Cube. And of course, you say, well, of course he wants people to solve puzzles. That's how he amasses his fortunes. Well, that's partially it, but I think that it's also true that, life is about understanding problems and learning how to solve problems. And problems take all different forms. Now, a lot of times people think math is just very dry thing, and it's just like, well, you have a bunch of numbers and you manipulate them. But math is more than just numbers. It's understanding and learning how to solve. And so there's a reason we want you here. And that's because we want you to become great solvers, great problem solvers. And not just numbers, but learn how to think and learn how to do well. Now, the goals for today, we're going to do word problems because those are important. It shows you, hey, there's this thing called the real world. And we have problems that we use words to describe. How do we transform them into math? And then, equations. And then we can do our tools that we have. We'll talk about lines, and particular graphing lines in Cartesian coordinates, and different ways to represent lines. All right, so that's where we're going. So, what are word problems? Well, blending two of our favorite subjects in college, math and English. A good combination. Say, okay, great. So, essentially it's just, again, problems in a different form. And so we have to learn how to translate. Read the problems and say, okay, how do we take these and turn them into something we can work with our tools that we've been developing? So there's sort of a game plan. You carefully read the problem. Sometimes, there's an aversion to reading. I'll just skim. I'll just look for some numbers, and I'll do a computation with the numbers, and life is good. No. Read it. Make sure you understand it. You can't solve a problem that you don't understand. So you have to understand it. Now, what are you looking for when you're reading? Well, you're looking for the things which might vary. And we give these variable-like names, x's or t's, or whatever the problem might recommend. We look for numbers. Numbers are a good clue. Say, okay, we'll keep track of those and how they relate to the parts which can vary. And a lot of problems will use the word is, and if you do have a problem which uses the word is, just remember is another way of saying equals. And it's like, if I see an is, what comes before the is, then there's an equal, and then what comes after the is. And that's usually a pretty easy way to set up a problem. Now, once we understand it, we write up our equation described by the problem. Sometimes there's multiple equations. And now we have put it into a setting we're comfortable with. So we carry out our tools. We manipulate the equation, our equations, and solve the problem. Now, once we're done, we've got to interpret the answer. We've got to go back and say, okay, we've got this thing that came out of the math. What does it mean in terms of our original problem? And is it consistent? Or do we get an answer which makes no sense at all? So that's what we're looking for. All right. So let's do maybe one or two warm-ups. So here we go. A golf course charges $52 for a round of golf using a set of their clubs. So in other words, you play the golf, and but all you do is show up, they give you the clubs. But they charge $44 if you have your own clubs. All right. Now, if you buy a set of clubs for $270, then how many rounds of golf must you play to recover the cost of the clubs? All right, now there's a couple of things. Of course, we like numbers, so probably we should mark these numbers. 52, 44, and 270 will all come into play. What's our goal? Well, if we buy the clubs and play a lot of games, then ideally we'll end up in the long run saving money. This happens a lot. You have to decide, there's two options. Either pay a big upfront cost and then have lower individual costs, or not pay the upfront costs but have higher individual costs. And the question is, what makes more sense? All right, so what do we do? Well, any suggestions on how to start? Let's ask this question. What is it we're looking for? Like the question says, what is it we want to find? Sorry, what? Well, okay, that's going to be part of it. But when we talk about our answer, like, what is our answer going to be? Rounds of golf, right? Because it says, how many rounds? Right? How many rounds? Okay, so that seems, if that's what we're trying to find, that should be one of our variables. It might be our only variable. So what do you want to call the number of rounds of golf? Now, we could just write number of rounds of golf every time, but that gets tiresome. So we write down names for these things. Let's come up with a name for rounds of golf. X? Okay. We can use X, we can use R, we can use G, we can even use emojis. It doesn't matter, but sure, why not? X. So X equals the number of rounds of golf. And this is for convenience. Now there's two scenarios. So let's talk about two scenarios. We use the course clubs versus we use our own clubs. Okay, so let's talk about the cost associated in these two situations. If we use the course clubs and we play X rounds of golf, how much will it cost us? 52X. Why? Because it's 52 if we use their clubs. For each round, there's X rounds. 52X. What if we use our own clubs? How much will that cost us? Sorry, what? 44X. Well, 44X, but there's something else. Plus this 270. Why the plus the 270? We have to have our clubs if we want to use our clubs. So we have to first buy our clubs, so there's a cost. And then, for every round, it costs us $44. So these are the two different amounts to play X round of golf. Now the question becomes, at what point does it make more sense? So, what do we want to be true? Well, what are we looking for when we compare these two values? Right, but how do these two relate? Like, I have two expressions. I want an equation. Is there what? I don't think that's quite what I'm going for. I guess my question is, there should be a symbol that goes in the middle here. What symbol am I looking for and why? If I put an equal sign, what would that tell me? That would tell me exactly X, right? Now, I'm going to hedge my bet a little bit because I think something's going to happen. So I don't want to put quite an equal sign. How many rounds must we play to recover the cost of the clubs? Well, that says we want to figure out how long it takes until it's less expensive to buy the clubs. So I want to figure out when is it greater than or equal to. So I'm going to use an inequality. And we'll talk about why an inequality can make sense here. All right. So we've put in this formula, 52x greater than or equal to 270 plus 44x. So if this is true for x, or maybe I should say for any x for which this is true, you're better off having bought your own clubs, because the cost for buying your own clubs is less than the cost of not. So for any x which this is true. So we're just trying to figure out, okay, so for which x's does this work? Well, what happens? Now we say we don't have to worry about this long, formulation, all these words. We have an equation to manipulate. So we put on our hat from last time. What can we do with this? Okay, so we can subtract 44x from both sides. 52 subtract 44. 8x greater or equal to 270. Now what can we do? Divide by 8, and since 8 is positive, we still keep our inequality. So x greater than or equal to 270 over 8. All right. Well, what's 270 divided by 8? Yeah, it's a number. It's a number. Does anybody have a calculator handy? I think it's 33 point, I want to say 875. Does anybody have a calculator? Sorry, what? 7.5. Dang it. Okay. 33.75. All right. I was off by 0.125. It happens. All right. So x is greater than or equal to 33.75. Now, why did I want the equals? Well, because what if I had a decimal point? What does it mean to play 33.75 rounds of golf? It's like, okay, well, I'm playing, and but I'm not going to play all 18 holes. I'll stop on the 14th hole. No. You have to play a whole round of golf. Okay, so we can't play a partial round of golf. So what's the answer? How many rounds must we play to recover the cost of the clubs? Sorry, what? 34. So we have to find some number that makes sense in terms of the problem. But we have to play a whole round of golf, so we need a whole number. So what's the first number? So we need to play at least 34 rounds of golf. Now, if we play more, great. We save even more money. But if we play less than 34, then we did not make a good investment. We should have just rented our clubs. All right. Any questions? Yes? Well, we haven't learned to graph yet. No. Okay. I think we can do one more. Let's push our luck. Relationship between Fahrenheit and Celsius. So this is your measuring temperature. And in different parts of the world, they use different systems of measurement. So Fahrenheit is predominantly used in the US, and Celsius is used pretty much everywhere else. So, all right, we have these two different systems, and it turns out they're related to each other in a nice way. So C stands for Celsius, F stands for Fahrenheit. So the relationship between Fahrenheit and Celsius is given by the formula. C equals 5/9 times F minus 32. Now, the good news is this, as far as word problems go, this is not too wordy. Solve for F in the above relationship. So notice here, if you look at this, we would say this has been solved for C, because you have C equals. So, if you see an expression that says like solve for something, what does that mean? It means that we want to get an F equals blah. That's the goal. So you want to isolate that one variable. Okay, so we don't need to look at part B, we can solve part A first. So we start with C is 5/9 times F minus 32. So, our goal, get F by itself. What can we do to start getting closer to our goal? Okay, there's this fraction in front. And so we can start by saying multiply both sides by the same amount. So 9/5 C. What happens when you multiply 5/9 times 9/5? It is the 1, right? By multiplying by the reciprocal, you get 1. And that's F minus 32. Now we're getting closer. We're getting F almost by itself. Not right there yet. What do we need to do? Add 32, right? If we add 32 to both sides, then we get F is equal to 9/5 C plus 32. Now, technically, I should have said 9/5 C plus 32 equals F, but it turns out that you can switch sides for the equal sign. And now we have this relationship. So originally, this works great. If you give me a temperature in Fahrenheit, I plug it in, I give you a temperature in Celsius. Now I can do the opposite. You give me a temperature in Celsius, plug it in, I can give you a temperature in Fahrenheit. Okay, there's a part B. Given that the range of temperatures in Celsius is between 20 and 30 degrees, what is the corresponding range for Fahrenheit? So, in other words, we are told the Celsius is between 20 and 30. What does Fahrenheit go between? How can we figure that out? Now, there's a couple of ways. So we just need one. So we could plug 20 in. Okay, so if you plug in 20 for C, this will tell us what the corresponding value for F is. So we get F is 9/5 times 20 plus 32. Well, okay, the nice thing is 5 goes into 20, so this would become 9 times 4 plus 32, because 20 over 5 is 4. And all right, 9 times 4 is 36. And 36 plus 32 makes 68. So this lower bound would be 68. What else would we do? Plug in 30. Now, I will say we are lucky here in that they sort of go in the same direction. Sometimes if they didn't, we have to do a little bit more subtle things, but certainly this is a reasonable thing for us to do. In this case, 5 also goes into 30. What is 30 over 5? 6. So 9 times 6 plus 32. 9 times 6, also known as 54, plus 32 makes 86. So between 68 and 86 degrees. I think that's pretty close to our weather forecast. So, all right, there you go. Okay, so we need to jump over and get to the other topic, which is lines. Well, we've been talking about linear equations. So specifically, we want to get into the visual representation of lines. And so how do we do it? Well, we're going to draw pictures. And to get there, we should first talk about the idea of Cartesian coordinates. Now, Cartesian coordinates is named after the philosopher Rene Descartes. You might remember him from such classes as I think, therefore I am. That's the one who came up with that expression. And legend has it, I don't know if this is true, but legend has it that one day he was sick and he was lying in bed. This was back before they had the switch. So, he didn't have a lot of entertainment. So as he was lying in the bed, he stared at his ceiling. And he saw a fly on the ceiling. And this provided hours of fascination for him. And he started to think, well, how can I describe where the fly is? And he said, well, I can just do it by a pair of numbers. How far is it over from this wall? How far is it from that wall? And that's the birth of the Cartesian coordinate system. To say, well, I'm going to start with this two-dimensional thing, we call it the plane, and we'll have a pair of directions and a central point. So we call the central point the origin. And the origin also known as 0, 0. And now we move some amount in the first direction. So let's say we move A in the first direction. And then we move some amount in the second direction. We move B. So we get a pair of numbers. We call this the coordinates. Now, the directions are traditionally called X and Y, but of course, I should point out there's nothing sacred about X and Y. You can change these to be anything you want. It's just convention. And don't be tied down to convention. Okay, so now I can put any pair of numbers as a point. All right, that's great. What if I have an equation? Well, when I have an equation, I might have many pairs of numbers that satisfy that equation. And so I can start putting point after point after point. I get this massive collection. And soon a figure emerges. And we call that the graph of an equation. It's all the places where the equation is true. Now, there's a special equation. AX plus BY equals C. This is a linear equation, the kind of equation we've been talking about. And when we graph such an equation, what happens? Well, what happens is that as we start putting in the points, we see that, unfortunately, I'm not a great artist, they come on and they make a line. So that's one of the reasons why we call this a linear equation, because, lo and behold, there's a line involved. And on a side note, if something asks you for what they call the standard form of a line, that's what they mean by standard form. AX plus BY equals C. This is not the most convenient, but this is what they'll call it. So if I have that equation, it's a line. And any line which you draw in this place, I can rewrite in that format. So now we have a way to look at lines. Now there's two very special cases. And that is, what happens if either A or B is 0? Well, if A is 0, what does it tell you about Y? If A is 0, what's true about Y? Oh. If A is 0, what's true about Y? Let's see, we probably have enough space, we can do this. All right, if A is 0, what's true about Y? You can either give a guess or a letter.
Horizontal.
No, that's not a letter.
A.
A. Okay, good, that is a letter. B. That's a good letter. E? No, I'm afraid not. What? W? I'm interested in what you're thinking of that word is. I need to keep drawing things, don't I? Okay, there we go. I? L? R? We'll draw little fingers here. Oh, yes. What? I think you want us to lose if you're guessing Z. Or do you have a word in mind that uses Z? A what? Okay. Z? This person can end up with like a 25 fingers here. H? What? C. U. D. N. Oh, that's a good choice. Constant. Yes, you got it. Nailed it. It's a constant, right? Because what do you see? Y is this thing which can vary, but B and C are numbers. So that says that Y is just a number, a constant number. It's always the same thing. So if Y is always the same value, then it says, hey, I'm always having the same value for Y. So you have to always be at the same height. So you have to be a horizontal line. Now, what happens if B is 0? Well, not that A is a constant, but X is a constant. So that says X has always had to be the same position. So it's always the same X value, same distance over. So it's a vertical line. So Y equals a number horizontal, X equals a number vertical. All right. So let's do a graph. Graph 3x minus 4y equals 12. So what do we need? What do we need? Now, is this a vertical line or a horizontal line? No. Both y's and x's are involved, so that's good. It's not vertical or horizontal. Now, if it was vertical or horizontal, it'd be quick. Just whoop, or whoop, just depending on which one. Okay, so how do we graph? How do we graph? Now, there's a strategy I would suggest. We know that this is going to be a line, because this is the standard form for a line. How many points do you need to be able to know for a line in order to get a graph for the line? 2. 2 points is enough information to make a line. So we just need to find 2 values for x and y that make a solution. If we do that, we win. Now, we could fumble around, but let's make it easy on ourselves. And you might say, okay, what do you mean by easy? Well, let's just choose some very convenient values for one of the variables and get the other. What's the most convenient number to pick? 0. So, let's pick x equals 0. If we pick x equals 0, what does the equation become? Minus 4y equals 12, or y equals negative 3. So this gives the point 0, comma, negative 3. So you come over here. You haven't moved anything in the x direction, but you're moving 3 points down in the y direction. So this is at the point 0, comma, negative 3. So we have 1 point. 1 is not enough, but it's halfway there. What's something else we can do? We can plug in 0 for y. So y equals 0. What will the equation now become? 3x equals 12, or x equals 4, because we can divide by 3. So what does that tell us? We're at the point x is 4, y is 0. So 1, 2, 3, 4. So this is the point 4, comma, 0. And now, what do? We just connect the dots. And there's the line. So to get a graph, find 2 solutions. And usually it's the easiest solutions are you just pick a value for x or pick a value for y and solve. Now I picked very particular values, namely I chose zeros for a reason, because I wanted to talk about something, which is that we have, these are very important places for a line. So this part right here, this is where the line hits the x-axis. That's a hard thing to say. And we call this the x-intercept. So if you want to find the x-intercept, you set y equals 0. So set y equals 0, solve for x. Now, there's also a point down here. This is where the line hits the y-axis. Any guess what we're going to call that one? The y-intercept, yes. How do you find that? Plug in x equals 0. So you'll oftentimes hear about x-intercept or y-intercept. That's where we're hitting the different types of axes. Well, great. So we have our line. Now there's a quantity that we like to look at for lines, which we call the slope. So the slope of the line, there's a couple ways to think about it. Sometimes in a very simplistic way, it's like, well, how steep is my line? And I like to say, well, the slope of the line is really telling you how your 2 different variables are related, because you have an x and a y. So as you change x, how much does y change? So if I change x, does y change a little, a lot? Does it go up? Does it go down? And the slope answers that question. So how do you compute this quantity? Well, the slope, which we use m to denote slope, it doesn't sound right because the word slope doesn't use the letter m at all, but we do. It's y2 minus y1 over x2 minus x1. I will say many people learn this as rise over run. So that's another way to remember it. But it's how much your y changes divided by how much your x changes. And so you pick 2 points. And this little comment here says, well, wait, which 2 points? And the answer is it doesn't matter. If I pick 2 other points, I'm still going to get that same ratio. So regardless of which 2 points you pick, the slope will be a certain value. It'll be the same value. And there's a couple of examples here. A slope of 0, that's our horizontal line. A small positive slope, you're going uphill, but not very quickly. A large positive slope, you're going uphill fairly quickly. Small negative slope, you're going downhill, but not very quickly. A large negative slope, you will go downhill very quickly. There's one other thing, which is if you have a vertical line, we say the slope is undefined. Some people might say it's infinity. So that doesn't sound like our class. So we'll say the slope is undefined. All right, so let's try an example. Find the slope of the line passing through the points -1, 5, and 2, 1. What do we do? What do we do? So we have our 2 points. So we can think of x1, y1 here, x2, y2 here. Yeah. Now it doesn't matter which point we say is the first or the second. So don't worry about it. It's like, wait, do I pick this as the first and this one as the second, or vice versa? Regardless of what you do, you'll always get the same number. It's really cool. So it's the change in y. So we can say 1 minus 5. Just whichever one you use as your first y and your second y have to be consistent with your x's. So 1 subtract 5, change in y, over 2 subtract -1. Be careful with your minuses. So upstairs, what do you have? 1 minus 5? -4. Downstairs, 2 minus -1? 3. Now, what do we do with this? We put a box around it because it's our answer. That's it. That's the whole thing. If you have 2 points, you throw it into the formula, out comes your slope. Life is good. Life is wonderful. All right, any questions about slope? Okay. Well, we've talked about the general form. So just as a reminder, we'll put it up here, general form. Or I think, actually, sorry, we didn't call it general form, we called it standard form. Standard form, ax plus by equals c. But there's some special forms, and these are the ones that you probably are more familiar with. So the first form is called the slope-intercept form, and it's because when you write it as y equals mx plus b. Where does the slope-intercept name come from? The m is the slope, and the b is your y-intercept. So if you happen to know your slope and you happen to know your y-intercept, it's like, I'm done. I can write down the formula. Life is good. So what are these two things doing to your lines? So what happens if you change b? So if I have a line, if I change b, what's happening to it? It changes the y-intercept. But the slope stays the same. So it's going to go basically moving it up or down. So b is sort of a vertical shifting of the line. Now suppose I leave b the same, but I change m. What will happen? Well, the y-intercept, let's say the y-intercept is right here, that'll stay fixed, but then it pivots. So those are the two actions going on with your m and your b. The other form is called point-slope form. So maybe you don't know the y-intercept, but you do know a point. So the y-intercept is like a spectrum. What if you know a point, but it's not on the y-intercept? Well, then you can say y minus y1 is equal to m times x minus x1. Where m, again, is your slope, so that's why we have slope. And then x1, y1 is a point on the line. Now, where does this come from? If you go back to your slope formula, you say, okay, well, m is your change in y over change in x. So I'm just using y and x as arbitrary points on the line. Change in y over change in x. Now just multiply by x times x minus x1, and you get your formula. So it comes from the slope definition. Now, these are nice ways to write lines, but there is a caution here. Not every line can be written in this way. In particular, vertical lines cannot be written in this way. So they have to be written in the form of x equals a number. All right, so an example. Find the slope-intercept form for the line through the point -1, -3, and 2, 12. So slope-intercept means we're shooting for this type of expression. So we need to know the slope, we need to know the y-intercept. Currently, what do we know? We know 2 points. And neither of them are the y-intercept. Oh. Duh. Okay, but what can we do with 2 points? We can find slope. So step 1, let's find slope. So we'll have this be our second point, this be our first point. What's going upstairs? What's the rise? Change in the y. So 12 minus -3, which becomes 12 plus 3. Downstairs, -2 minus -1. So we get 15 upstairs, 3 downstairs, or 5. All right, so almost always, if all you have is 2 points, start by finding the slope. That's a good strategy. Now, I have a slope, and I have 2 points, and I have 3 different ways to write the line. What can I do next? Which one of these 3 can I go to? I can go to this third option, this point slope, because I have a slope and I have a point. Which point do I need to use? It doesn't matter. You'll get the same thing either way. So which one do you want to use? Now, again, it doesn't matter, but you have to make a choice. 212? All right, we'll use 212. So y minus the y-coordinate 12 is equal to m, which is 5, x minus the x-coordinate, which is 2. Now, is this our answer? No, because it doesn't look like that. So what do we need to do? We need to make it look like that. That's what we need to do. How do we get there? We can distribute the 5. So this becomes 5x minus 10. What else do we need to do? So this gives us y minus 12 equals 5x minus 10. We're closer, but not all the way yet. Add the 12. Because our goal is, really we're trying to solve for y. So we say, okay, so y equals, when we take negative 10 plus 12, we get 2. Is this our answer? Yes, right? Because it looks like y equals something times x plus something. So, if I ask you, what is the y-intercept, what do you tell me? 2, because I'm pointing at it. If I ask you, what's the slope, what do you tell me? 5. Now, suppose I said, find the standard form. What would you need to do? Because you want to get the x's and y's on both sides, so if you subtract 5x, you get y minus 5x equals 2. So you can get to standard form. So in some sense, even though we introduced standard form first, it's easiest to sort of work your way slope point, then slope intercept, and then up to standard. And all right, well, I think that's pretty much our time. So we'll stop here.